Okay, in this lecture we will discuss about the type 2 PLL. But before we go to the different type of PLL, let us try to understand what are the drawbacks associated with the type 1 PLL that we have discussed till now. Okay, so drawbacks of type 1 PLL with JOR as the pest detector. Okay, so the main drawback is the limited equation range. Okay, so equation range, sometimes this equation range is also called as tracking range or log range, sometimes it's also called as log range or capture range, right? So what it means is that if there's a large difference in the omega in and omega out of the PLL, right? If there's a large difference between the omega in and the omega out of the PLL, the it will not be able to log. Okay. Moreover, to get the average value for some DC voltage, right? We also should make sure that there should be a sufficient phase error, right, to get that voltage. So that also creates a problem. Okay, so let me demonstrate what I'm telling about the limited equation range. Okay, so this is the one. Okay, so of course we have seen the last time that the PLL is logged here very nicely. Okay, but suppose if I change the frequency, input BREF frequency, so this is 1 megahertz, and suppose if I make it 0.9, okay, so it is supposed to log at 0.9. Of course it will log. Okay, so if we want to know whether it is the output frequency is 0.9, we can see that this one here, we can get an FFT of this one, view the FFT of only V out. Okay, so and if we zoom in here, we'll see that it is, yes, it is exactly looking at 0.9 megahertz or 900 kilohertz. Okay, so now suppose if I again further decrease it, right, the output is supposed to track it, right? So we can see that of course it's still locking, right, but and you can see that the control voltage is decreasing to get that particular particular frequency. But if I further reduce it to maybe 7 megahertz, zero point 0.7 megahertz, so you can see that the control voltage starts oscillating and it is not able to lock. So the range is very small. Or if I go higher to 1.1 megahertz as well, 1.1 megahertz as well, so you'll observe that it is not able to lock. See, it's not locking, right? So the locking range is very limited. And of course what will happen in the actual scenario, that there can be variation in the frequency characteristics or the cavity characteristics of the PCO because of different variation in an IC, right? So and if the variation is very large, so the PLL will not be able to track. Okay, so this is one of the main drawback with the limited equation range. Okay, of course this is some more other drawbacks, like for example we have discussed about the the trade-off that there is a trade-off between the settling time and the ripple voltage. Okay, so this we had discussed in the last class. Okay, moreover there is a constant phase difference between phi in and phi out. It requires a constant phase error to generate the average voltage to operate the VCO at a certain frequency. So this is also one of the drawback. So all this drawback we'll try to see how to get rid of them, especially the this one, the limited equation range, and as well as the the constant phase difference between phi in and phi out. Okay, so let's discuss the type 2 PLL. So type 2 PLL with charge pump. So again, we'll see why this is called a type 2 PLL, and we'll also see what is a charge pump. Okay. So basically what we are trying to do now is that to get rid of the limited equation range. So especially what happens is, if the frequency difference between the input and output is very large, so we should have some mechanism to bring the two frequency very close, and then we can go for the phase locking. Okay, so this leads to another loop that we need, right, which is doing the frequency detector. So what I mean is, currently what we have designed is we have the phase detector PD, okay, and we have the low pass filter, okay, and of course it is driving the VCO. So what I will do is I will just sort of VCO here, okay, and we had taken the this is the input signal, and the output of the VCO is coming, and to the phase detector, and of course this goes here, something like this, and here. Okay, so this is my, of course this is my V in, okay, and my after the VCO, the V out is coming from here. Okay, so this is my V out, and which I'm feeding it back. Of course we are not using a divider for simplicity. We will discuss what happens to the divider maybe eventually if we put a divider, how all the transfer function changes and all. It's very easy. So once we understand this loop dynamics with learning or understanding the loop dynamics with divider is very easy. Okay, so this is what we have discussed till now. So what we want is, if there is a large difference in the frequency between V in and V out, we want it to detect the difference in the frequency and log it first. So what basically I want is, I want an something like this, a frequency detector, so which can find out the difference between this frequency and quickly tell the VCO that look, the frequency is, there's a lot of difference in the frequency, so bring the omega in and omega out very small, the difference between them very small. But of course, even if as we has mentioned that FLL doesn't work, right, because we cannot make it perfectly same because of there can be an offset, right. So this is what we had discussed. So just a STEL alone FLL is not going to work. Okay, so we need the combination of both. So again, as we have seen that only the PD doesn't work because if there is a large frequency, if there's a large difference in the omega in and omega out, then the loop doesn't lock. But whereas in this case, if we have the FLL, if there is a large difference between the omega in and omega out, it can bring very close to it can make the difference very small, but it cannot make it equal. Okay, so these are the two advantages and the disadvantages of the only with phase detector and only with a frequency detector. So what we want to do is we want to get a hybrid architecture, or I should say a combination of both, right? We can have both a phase detector as well as the frequency detector. When the difference in the frequency between omega in and omega out is very large, we can use this loop, and when omega in and omega out becomes very close, we can use the phase detector. So how do we club this? So we can club this very easy way. What we'll do is that of course we'll have a single VCO, and okay, so we'll have one FD. So whatever the diagram that I have shown, we can just reverse it, okay? And again, it will also have a low pass filter, okay? LPF, and this can go something like this, the control voltage, and I can use an adder here. Of course, the output also has to be given to the frequency detector, and this, of course, this can be LPF1, LPF2, because this can be two different low pass filter, okay? And okay, let's erase all of them, and this I should give the V in also to both of them, okay? So this will be my V in. So of course the corresponding frequency is omega in, and the corresponding that is coming out is omega out, okay? So yeah, so I have two loops to control the VCO. So initially, when omega in and omega out are very much different, is that the phase detector will not be working, and it will just control and set the VCO voltage such that the omega in and omega out is very close. And once this is done, once omega in and omega out are very close, the phase detector will stop working, and the phase detector will work, and it will try to precisely match and bring omega in is equal to omega out. So basically this is like a coarse tuning. This is like a coarse tuning, and this is like a fine tuning, right? Yeah. Okay, so now let's try to understand how can we get a circuit something like this. So in actual sense, what we are going to do is that we are going to club both of them, and we are going to get a phase frequency detector, okay? So the next thing that we are going to study is the phase and frequency detector. So what we are going to do is that we are going to get a single block, so which is going to act as if it is a frequency detector when omega in and omega out is very large, and we can have and it can act as a phase detector when omega in and omega out is very small, okay? So this is the PFD, okay? So of course the input of the PFD is there will be two inputs, where let's call this input A, and let's call it as input B, okay? So input A, we know that it is the reference, and of course the input B will be coming from the it will be coming from the output, okay? PFD, it is the short form for this one is PFD, phase and frequency detector, okay? So now we are going to introduce a, we are going to introduce some state of the output, okay? So this will give me two outputs, okay? This is QA and QB, okay? So QA and QB is something like, if if suppose the frequency of A is much higher than B, then QA will give high, or the average value, whatever the out of QA will be very high, okay? And whereas the QB will be silent, zero, Similarly, when the frequency of B is higher, okay, so this will give a very large average value of 1, whereas this will be 0, okay? So like that. And and whereas if QA and QB are equal, they're almost the same, then it should spit out both 0 0, okay? So these are the three states of the this phase frequency detector, right? So so again I'm repeating it. So if A is much higher frequency than B, then QA will be 1 and QB will be 0. Whereas if B has a much higher frequency than A, the vice versa is going to happen. QB will become 1 and QA will be 0. Whereas if both of them have the same frequency, then both of them will be 0. Okay, so basically I have a 3 states. Okay, so I can represent this whole thing by 3 states. Okay, so how is that, like? So QA is equal to 1 and QB is equal to 0 when frequency of A is higher than B, whereas QA is equal to 0 and QB is equal to 1 when frequency of B is higher than A, and QA is equal to 0 and QB equal to 0 when frequency of A is equal to B. Okay, in the previous phase detector, so what we used a jaw, and jaw was basically trying to compare the levels. Okay, so the output of the phase detector was dependent on the levels, but we know that when we want to try to find out the frequency content of a waveform, the better approach is to suppose I have this waveform, right? I have this clock waveform. So if I want to know the frequency content of this waveform, it is better to look into the zero crossing or this rising edge or in the falling edge, like, or one of them, right? So whereas in the previous phase detector, what we are trying to see, we are trying to compare the levels, and which was not very accurate, and because of which it had a limited range. So now what we are trying to do is we are trying to compare the I should say that the rising edge. Suppose this is one clock frequency, and the other clock frequency maybe something like this, maybe much smaller. Okay, right? So you can see that this is a very the clock frequency is much lower. So what I can do is that I can try to compare the rising edge, right? So what I will do is we'll try to compare the rising edge and see which has more rising edge and which has a lower rising edge. Okay, so let's call it this omega A and omega B. So basically we are trying to compare. Okay, so what we so now we have we have these 3 states. So we can define, or we can make a finite state machine, something like this. So we'll design a finite state machine which has these 3 states. Okay, QA is equal to 0, QB is equal to 1. Okay, so this state, and this I will call it as, here I'll write it here, QA is equal to 1 and QB is equal to 0, and the middle state is this one where QA is equal to 0 and QB is equal to 0. Okay, so so this is the state when my B or the B has a much higher frequency compared to A, and this is the state when A has much higher frequency content than B. Okay, so now what we'll do is that initially, suppose if it is in 0 0, if this is the starting point, and if I see a rising transition in B, right? If, or let's consider this case, if I have more rising transition, so as soon as I see a rising transition, right, in A, I should go here. Okay, So whenever there is a transition, then so transition or a rising edge, then it should go to here. And if it is again seeing one more rising edge, okay, let it stay in this state only, okay. So like that, okay. But whereas if it sees a rising edge in the B, then we'll come back here, okay, something like this, okay. And whereas same thing vice versa happen if I see a rising edge in B, okay, then I will come here, and if it sees a rising edge in A, then it will come back here. And if it sees a rising edge in staying here, if it sees a rising edge in the B again, it should stay in this state, okay. So this state machine can this state machine can take care of this one. For example, if suppose if it has if the A has a lot of rising edge, then it will go here and it will keep on staying here, okay, telling that the frequency content of A is much higher, whereas the vice versa will happen. If there is a lot of rising edge, it will come here. Whereas if there is an equal number of rising edge in A and B, then what will happen? It can go here and come back here, and once it see rising edge in A, it will go here and come back here. So overall, it will try to stay here. Okay. So let's try to demonstrate this one with an example. Of course, it may not be very clear now, but with an example, we'll try to make things more clear. Okay. So let's consider an example. Okay. Okay, so suppose I have a waveform something like this. So this is my omega A, okay, and let me draw a omega B as well. So what we want to see is, suppose both of them are having very close frequency, okay, almost the same frequency, but there is a phase error, okay. So of course, because this is going to act as a phase detector as well, so what I should say that I should be able to get my QA should have more average value compared to the QB, or QB should be silent, okay, because here what we are going to do is that the phase of the A signal is leading than B, then also it should give QA to be higher than B, because it's also should act as a phase detector. So in this case, what is the case when my phi A is not equal to phi B, so when the phases are not aligned. So now if you see here, because of the rising edge here, right, so what I'm going to do, I'm going to get is that my QA will be high, and when it sees the next rising transition, it will come to the 0 0 state, okay. So this is my QA and QB, and from here to here it's 0 0. So when it sees a rising edge, okay, in the A, it is going to the state when QA is 1 and QB is of course 0, and when it sees the next rising edge in B, it should come to the 0 0 state. So QA was 1 momentarily, because I can see a transition rising edge here, and once it see a rising edge in QB, it is 0. So the same thing is going to happen here as well. So again, once it see a rising edge in QA, it will go high, and again it will go go back to 0. And of course, QB in this case is 0, and this same thing is going to repeat here as well. So you can see here, if the average value of QA is higher, telling that QA is leading QB. So this is actually acting as a phase detector, and this is the case when my QA and QB, the phases are not same, but where the frequency is, I should say, same or almost similar, okay. So this is acting as a phase detector. So let's see when it acts as a frequency detector, and when the two frequencies are not the same. So let me call it as a case 1. So now let's go to the case 2, when the frequency of these two frequency omega and omega b are very different. Okay, so in this case they are not same, and we can see that the frequency content, right, frequency content of omega a is much higher than omega b. Okay, so, or to generalize it, we can just say that omega a not equal to omega b. Okay, of course in the other thing, the reverse is going to happen. If if the b is leading than a, so I'll have more pulses here, and it is going to become 0 if you follow this state machine. Okay, let's try to follow this state machine and try to plot the qa and qb for this. Okay, qa and qb, right? So in this case also, because the frequency content of a is higher than b, so the qa should have more pulses compared to qb. Okay, so now of course, as soon as we see this rising edge in qa, so whenever we see a rising edge in qa, so it should go to qa equal to 1 and qb equal to 0. So it will go to the state of qa equal to 1, and qb is of course 0 here. It's going to 1 here, and as soon as it sees a rising edge in b, it should come back here. Okay, come back to the stage of 0 0. Okay, so the now if we go ahead, the next rising edge of this a is here. Okay, so similarly it will go again high here. Okay, and in the next rising edge of b, the qa is supposed to go again to the state 0 0, and of course qb, there is no in this case we have never gone to this state, right? qb is never 1. Okay, we are just analyzing the state when qa is 1. Okay, or it has it is seeing the rising edge of the a before then b. Okay, again here also once we see the rising edge here again, so we can see here that it is again it will go high, and in the next rising edge here it's going to go to low. Okay, and again here where it's going to go high again here, and in all these cases you can see that the qb will be always 0. So here also you can see that if you see the average value of qa, it's going to become much higher compared to the qb, or qb is almost 0 and it has a dc content. Okay, so by this also, by seeing the dc content, or we can say that qa has a higher frequency compared to b. So here what we are trying to detect is that whether out of the two waveforms, which one has a higher frequency content and the other. Also here we are seeing that who is leading and who is lagging. Okay, so whenever there is the difference in the phases, okay, then also what is going to happen is that the frequency content of a and b are, a is going to become higher than b, or vice versa. Okay, and we can see that when these two rising edges they fall in the same place, okay, means the two waveforms are having the same frequency as well as there is no phase difference, then only theoretically this qa and qb will be 0, or we can go to, will be in this state. Okay, yeah, so the complete opposite can happen, right? If the frequency content of b is higher than a, then of course I'll have more pulses here, right? So because it's a symmetric, so the same thing will happen for b. Now the next question is, how do we implement these this kind of state machine? Okay, so how can we implement this? A very easy way to understand is, because we are trying to do the edge detection, okay, edge detection, and edge detection can be done only by a flip-flop. So we definitely have to use a flip-flop, okay. So we will be using two flip-flops, okay, because we are detecting two signals here. So we'll be using a two flip-flop and one gate, and this will implement this particular frequency phase detector, and the circuit is very easy, okay. So let's see on the implementation of the PFD. So this is my D flip-flop, D, then this is the output Q, and this is my clock, okay. I'll be providing a clock here, and here basically we need two D flip-flops, okay. One D flip-flop for detecting the rising edge of the A, and the other D flip-flop for detecting the rising edge of B. So what I'll do is that I just reverse it and just, you know, write it in a reverse fashion, okay. And this is my Q, okay. So now what we'll do is that, of course, this clock will be given to the signal A, and this clock will be given to the signal B, okay. And here I'll be using the reset, okay. So this is a reset pin that is there for the D flip-flop, okay. So I'll be using a reset, and what we'll do is that the D will be always connected to the VDD or logic 1, okay. And similarly this D also will be connected to the VDD, okay. And this will be my QA, and this will be my QB, and there will be an AND gate, okay. So this is the, you know, this is the implementation of the PFD or the state machine that we have seen before, okay. So let's see whether it works that way or not. So let me copy paste this state machine and see whether this is following this one or not, okay. Okay, so if you see here, right, so if it suppose initially both of them are 0 0, both of them are in this state, so QA is 0 and QB is 0, okay. So if this is a rising edge in A, rising edge in A, because the D is always connected to VDD, the QA will become 1, okay. QA will become 1, and 1 and 0, the end, so it's 0, it's not resetting. So this reset pin is a hard reset, so this is not edge triggered. That means whatever the state it may be, like if it is 1, like whether there's a clock edge or doesn't have a clock edge, as soon as the reset is 1, it's going to reset both these, you know, D flip-flops. Okay, so now suppose I have gone to this state where my QA is equal to 1 and QB equal to 0. Now if again it sees a rising edge, definitely it stays 1. So it will keep on circulating this one, right? So if it is 1. Now if it sees a rising edge in B, it's a rising edge in B, so that means this is going to become 1. Okay, this is going to become 1, and then 1 1 and 1 is going to become 1, okay. Then it's going to reset both of them, and QA and QB will be 0, okay. 0 0, so basically it's coming back to this state, okay. So if it is rising edge, it's just a rising edge in A, then it goes to state A, this state, okay, where QA equal to 1, QB equal to 0, and if it sees again one more rising edge, it's going to stay stuck here, and as soon as it sees a rising edge in B, it's going to come back to the state 0 0, okay. So same thing is going to happen this side as well, because it's a perfect symmetry here, if you can see here. So if it is in a 0 0 state, and if it sees a rising edge in P, right, rising, it's going to go here, this is going to become 1, right, this is going to become 1, and of course this is still 0, okay. And if it sees another rising edge, then it will stay and keep circulating here and be in this state. And as soon as it sees and rising edge in A, then this will become 1, okay, this will become 1, and after 1 then this becomes 1, and both of them will be reset and it will come back to 0, okay. So both of them will become 0 0, okay. But if you see, if you observe here, you must have observed here, right? So if you are coming from this state to this state, right, so you will see that there is some momentary, there can be a delay, because there will be a gate delay. First these two are becoming 1 and 1, you will see, right, 1 and 1, and then this becomes 1 from 0, okay. And then the reset is fired. So from reset to Q there can be a slight delay. So this we'll understand when we'll just draw a waveform of this one. We'll try to understand this point by drawing the waveform in the next page. So we will now see the effect of the delay or the gate delay. Okay, so this is the maybe the signal at A, phi A, okay, and I just copy paste it. This is, maybe let's call it as this phi B, okay, and of course we'll have the signal QA and QB. Now of course the rising edge is the focus. So now in the first rising edge the QA will be high, okay, or let's maybe make the delay a little more, okay. So then my QA will become high, okay, and of course my QB is 0 here, and as it goes, because of the rising edge here, right, so in this case the QA is 1, QB is 0 now, and of course this is 0, but then because of this rising edge, okay, because of this rising edge here, so momentarily this will become 1, okay, so 1, so for a small pulse it will become 1, okay, and then after some time this is 1 1, so this becomes 1, and it is both the D flip-flops are reset, okay. So that means this will come down, okay, so this will come down something like this here, and this also comes down, okay. So because of the gate delay, okay, there will be there will be a small pulse in QB, and this duration will be the delay. This TD will be delay from end and reset to Q delay, okay. So the delay that is given by this AND gate, and of course from reset to Q, right, in practical circuit, if the reset is 1, it is not immediately that this will be 0. Okay, there will be some time it will take for this Q to be 0. So this is the TD. Okay, and similarly, of course, here also the same thing is going to happen. Okay, so of course, sorry, in my drawing, these are the these delays are different, but actually in real sense they are same. Okay, so although there is small pulse because of the delay, but this doesn't cause any problem that we will see, because eventually the what we are going to see is the average value of this one minus average value of this one. So eventually this is taken care of. So even if there is a small pulse because of this delay, that will be taken care of as we study the charge pump. Okay, so with this we'll end the discussion on the frequency and the phase detector. In the next lecture we'll try to see how do we convert this pulse width into voltages using a charge pump.